Hey guys, welcome to my channel Dr. Krishna. Now in today's presentation we are going to learn about generalization of Cayley Hamilton theorem for the polynomial matrices. I know a very long name for this presentation, but let's not waste any more time and dive into our presentation. For that I want to let you know that my name is Sai Krishna. So let's know about me first. Well, I'm a student who is pursuing data science bachelor's degree at IARE. It's enough for you, I guess. Now let's move on to objectives of today's presentation. Now, the first objective of today's presentation is introduction to Cayley Hamilton theorem. First, we will learn what is Cayley Hamilton theorem and what is its formula. Next, we will watch the founders of Cayley Hamilton theorem, since we need to respect the people who discovered this theorem. Next, application of Cayley Hamilton theorem. So where does we use this Cayley Hamilton theorem? We must know. Then we will be capable enough to understand the generalization of any polynomial matrices using Cayley Hamilton theorem. So let's move on to our first objective, which is introduction to Cayley Hamilton theorem. Introduction to Cayley Hamilton theorem. In linear algebra, the Cayley Hamilton theorem states that every square matrix over a commutative ring, such as real or complex field, satisfies its own characteristic equation. A is a given n by n matrix and n is the n by n identity matrix. Then the characteristic polynomial of A is defined as P of A is equal to det of x times of I minus A. So this is characteristic polynomial of A. So what does this essentially mean? We all have learned what is characteristic equation of a matrix. It's generally A minus lambda I, mod det of A minus lambda I equal to 0. So what this Cayley Hamilton theorem states that is lambda is A, means a matrix is the its own zero of characteristic equation. Now, if you break down the equation, that is A minus lambda I mod equal to 0, you can find that you can find by equating that A is equal to lambda. So the Cayley Hamilton theorem just states that in verbal form, it is that is lambda is A. Now, where that is the determinant operation and is a scalar element of the base ring. Since the entries of matrix are linear or constant polynomials in lambda, the determinant is also an nth order monic polynomial in lambda. So what he is saying is that the polynomial which we will get by equating characteristic equation has the degree equal to the order of the matrix we reference upon. This statement is wants to say that. Now, the Cayley Hamilton theorem states that substituting the matrix A for in this polynomial results in the zero matrices, that is P of A equal to 0. Essentially, what it says is there is a way and there is a chance that lambda is equal to A and P of A, which is characteristic equation solution, is equal to 0 when you substitute A in the place of lambda. The powers of A obtained by substitution from powers of lambda are defined by repeated matrix multiplication. The constant term of P of x gives a multiple of the power of A, which power is defined as the identity matrix. The theorem allows AN to be expressed as a linear combination of low matrix powers of A when the ring is a field. The Cayley-Hamilton theorem is equivalent to the statement that the minimal polynomial of a square matrix divides its characteristic polymer. I know it's very hard to understand and perceive, but it simply states that A is the zero of characteristic equation. Simple. The whole concept of a Cayley Hamilton theorem is its own matrix where A is the zero of its own characteristic equation. Just don't make your head go around. It's the basic thing that we want to know and we want to convey. Next, now the theorem was first proposed in 1853 in terms of inverses of linear functions of quaternions, a non-commutative ring by Hamilton. This corresponds to the special case of certain real 4 by 4 or 2 by 2 complex matrices. The theorem holds for general quaternionic matrices. Cayley in 1858 started it for 3 by 3 and smaller matrices, but only published the proof for 2 by 2 case. The general case was first approved by Frobenius in 1878. Now, what he wants to convey, what his slides is conveying to us. The theorem was first developed not to solve the things that we solve right now. It was mainly developed to solve complex matrices of order 4 by 4 or 2 by 2, but not really 3 by 3. As the time went on, the proof to solve 3 by 3 also came into existence and was first proved by Frobenius in 1878. This gives us a brief history of how Cayley Hamilton theorem was first discovered and then how it was molded to find applications. So my slide, we are officially completing our introduction part to Cayley Hamilton theorem. Now I will meet the founders of Cayley Hamilton theorem. Arthur Cayley, 1821 to 1895. He was a British mathematician. He helped found the modern British School of Pure Mathematics. He entered Trinity College, Cambridge, where he excelled in Greek, French, German, and Italian, as well as mathematician. He worked as a lawyer for 14 years. Wow, what a career and what a resume he has, right? He is a multilingual person along with lawyer's degree and a mathematical mind. So at his time, he may be the most fearsome lawyer, I guess. He postulated the Cayley-Hamilton theorem that every square matrix is a root of its own characteristic polynomial and verified it for matrices of order 2 and 3. He was the first to define the concept of a group in modern way as a set with a binary operation satisfying certain laws. Now, the last point doesn't concern today's presentation, but it's important to know that he was a mastermind to create a concept called group, which then led on to have binary operations based on certain criteria he proposed. So this is the brief history of one of the founder, Cayley Hamilton here. Cayley Hamilton. He was a multilingual, charismatic, good lawyer, and a fearsome one. So let's move on. Let's meet the next lawyer. Is Sir William Rowan Hamilton. 1805 to 1865. He was an Irish physicist, astronomer, and mathematician who made important contributions to classical mechanics, optics, and algebra. His studies of mechanical and optical systems led him to discover new mathematical concepts and techniques. His best known contribution to mathematical physics is the reformulation of Newtonian mechanics, now called Hamilton mechanics. This work has proved central to the modern study of classical field theories such as electromagnetism and to the development of quantum mechanics in pure mathematics. He is best known as inventor of quaternions. He is also a great man if you ask me. He is a scientist by nature by profession and also a great mathematician who was able to formulate Cayley Hamilton theorem. So his best niche are mechanics, optics. So, and his best contribution to the society was in quantum mechanics, and he is best known. I guess he has a nickname in the science culture or science groups, that is inventor of quaternions. Now, most of us don't even know what it is. So let's move on. By this slide, we are finished with the founders. Well, at that time, these were really good people, I guess. They have very diverse taste. Let's move on to the next topic, that is theoretical applications of Cayley Hamilton theorem. So, what are the theoretical applications of Cayley Hamilton theorem? First, inverse and power of matrix. That's it. Cayley Hamilton theorem is mainly used theoretically for finding inverse and power of a certain matrix. Now let's move on to practical applications of Cayley Hamilton theorem. Matrices are used in many fields like robotics, automation, encryption, quantum mechanics, electrical circuits, field visualization, including etc. All places would require powers of the matrix or inverse. Cayley Hamilton theorem helps in expressing the inverse as a polynomial expression of the matrix, higher power of the matrix in terms of the lower power of the matrix. Next. The Cayley Hamilton theorem and its generalization have been used in control systems, electrical circuits, system delays, similar systems, especially in the DC circuit. So, we do not know actually what are the applications of matrices, right? Matrices are a way to store data and extract them whenever with certain conditions. It works best while extracting data and while storing data. So the applications are those where extracting data in a particular condition makes it more optimal. If you observe, if there is an application called system with delay. So in this application, what happens is the data or the signal is stored inside a matrix, and the processing power is tuned in such a way that it takes some time to process it, and matrix will make sure to make it that complex that it takes a certain amount of time for the processor to process it and transmit the signal. So as I have said, matrix is a way to store data and retrieve it with certain conditions. Using this property and with Cayley Hamilton theorem to assist those conditions of extraction, there are diverse applications for Cayley Hamilton theorem along with matrices. The most widely used industry is electrical signal processing industry. By this slide, we have officially completed with theoretical and practical applications of Cayley Hamilton theorem. Now, let's move on to more cliche and the important topic of today's presentation, that is generalization for ND polynomial matrices. Let the ND polynomial matrix be invertible and let hold them. Now, whatever you are able to see here is the formula or is the generalization of ND polynomial matrix on the basis of Cayley Hamilton theorem. Here, let's see the notations, where the AI are the real coefficients of ND polynomial and Nk, where k is equal to 1, so on to n, are non-negative integers. So what are the applications of generalization for ND polynomial matrices? To solve the discrete time linear systems with H, where H is greater than 1, time delays described by the equation given below. As I have said, in the practical applications of Cayley Hamilton theorem, the delay of signals is a huge is a huge application for matrices. Now, generalization for any polynomial matrices make it more efficient and useful to process signals with certain delay. And the given equation suggests how to perform that action. Next application is to solve 2D linear systems described by the equation. So here, yeah, it is very theoretical, not so practical, but these theoretical formulas will be an integral part of a certain practical solution which we will have in coming days. Let's think. As I want to stress more on signal processing with delay. Suppose suppose what we use is countdowns. Essentially, we use countdowns. In what use cases? While detonating a building, there will be a countdown. But what happens if a countdown fails? Moreover, we have atomic clocks on satellites, which on real time have accurate time, as we know it. But these can also get failed. Now, this if this uh, generalization helps to make the delay process more efficient and more accurate, then there will be no need of mechanical atomic clocks, or there will be no need of digital or mechanical counters. It just happens. Why, how, and why? Well, the processor is designed in such a way to process it at a certain time, and the matrix, and with some certain conditions using this Cayley Hamilton Theorem generalization, can help to delay the signal even more. So I guess this is one of the biggest applications for Cayley Hamilton Theorem, specializing in generalization of ND polynomial matrices. By this slide, I complete my presentation. So let's move on to the summary. So what we have learned in today's presentation. Introduction to Cayley Hamilton Theorem. First of all, we know what is Cayley Hamilton Theorem. Next, founders of Cayley Hamilton Theorem, and these people are very good in their fields, truly multi-talented. Applications of Cayley Hamilton Theorem. Yes, there is one theoretical application and some practical application. Then generalization for ND polynomial matrices, which is specialization of Cayley Hamilton Theorem. So, what are my opinions? Well, the classical Cayley Hamilton Theorem has been extended for real polynomial matrices in n variables. It has been shown that the known extensions of Cayley Hamilton Theorem are particular cases of the proposed extensions. The application of the proposed extension has been illustrated by the examples which I have already shown you in the application part of generalization for any polynomial matrices. So, I'm resting my presentation. Thank you for listening with me. Have a nice life. Sayonara.